All right, let's dive into one of the most important skills in all of chemistry, balancing chemical equations. Honestly, think of it like learning the grammar of a new language. Once you get the hang of it, this whole new world just opens right up. So let's get started. So here's what we've got on tap today. We're going to start with the big, unbreakable rule that makes this whole process necessary in the first place. Then we'll walk through 3 different ways to do it, from the simple stuff to the real heavy hitters. And finally, we'll get to the aha moment, what those numbers we're calculating actually mean. But before we get into the nitty-gritty, let me ask you a question. What could a campfire possibly have in common with a baker's kitchen? I mean, they seem totally different, right? Well, it turns out they're both run by the exact same unbreakable law of the universe. And that law is why we're here. This isn't just some made-up rule for your chemistry homework. This is a fundamental principle of how everything, and I mean everything, works. It's called the law of conservation of mass, and it's actually really simple. You can't just create matter out of thin air, and you can't make it disappear. Whether you're burning a log or baking a cake, every single atom you start with has to be accounted for in the end. It might get rearranged, but it never ever just vanishes. So this brings us right to the heart of it. A chemical equation is really just the story of a transformation. And for that story to make any sense, the number and the type of atoms you start with, we call those the reactants, has to perfectly match what you end up with, the products. That's our entire goal here. Okay, so how do we actually do it? Let's start with the most direct method, sometimes called balancing by inspection. Really, it's just like taking inventory before and after something happens. Let's check out a reaction between magnesium and hydrochloric acid. We can set up a simple little table to count up our atoms. And right away, you can see the problem, can't you? We start with 1 hydrogen and 1 chlorine on the left, but we end up with 2 of each on the right. The books just don't balance. Now, the only thing we're allowed to change are the big numbers out front. Those are called coefficients. We can't change the little numbers. So by putting a 2 right in front of the HCl, look what happens. Our count for the reactant suddenly changes. Now we've got 2 hydrogens and 2 chlorines on the left, which perfectly matches the right. And just like that, the equation is balanced. Okay, that tally method, it works. It's solid. But let's be honest, it can get pretty slow with more complicated equations. The good news is there are a couple of pro tips for common situations that can save you a whole lot of time. We're going to focus on 2 key shortcuts. First, how to handle these groups of atoms called polyatomic ions that like to stick together. And second, a really slick trick for a super common type of reaction, combustion. All right, shortcut number 1. At first glance, an equation like this can look like a total beast, right? You see all these different letters, and it just seems like it's going to be a huge pain to count everything up one by one. But there's a secret here. Look really closely at that NO3 group, the nitrate ion. See how it appears on the left side, and then it shows up again on the right side, totally intact? It's like a little team that sticks together. So the trick is to stop counting individual nitrogens and oxygens. Instead, just treat the whole NO3 group as one single item. That makes the whole puzzle way, way easier to solve. Our second shortcut is for combustion reactions, which is just a fancy way of saying burning. And when you burn a hydrocarbon, that's just something made of carbon and hydrogen, it always follows this predictable pattern. It reacts with oxygen and always makes carbon dioxide and water. And that predictability is what gives us this great little trick. And here is that trick. You have to balance in a specific order. First you do carbon, then you do hydrogen. After that, you count up all the oxygen atoms you have on the product side. Whatever that number is, you take half of it and put that in front of the O2 on the other side. Now, if you end up with a fraction like 7.5 or something, no worries. You just multiply every single coefficient in the whole equation by 2, and that'll clear it right up. But what about those truly monstrous equations? You know, the ones that seem almost impossible to solve just by looking at them? For those, we need to break out the power tools. Welcome to the algebraic method. Now, don't let the word algebra scare you off. The math itself is actually pretty simple. The whole strategy is just to turn our chemistry puzzle into a little system of equations that we can solve step by step with no guesswork. So step 1 is easy. Instead of trying to guess the numbers, we just assign a letter, a variable like A, B, or C in front of every single compound in the whole reaction. Next, we take that unbreakable rule, the law of conservation of mass, and we turn it into algebra.
We make a rule for each element. So let's take potassium, K. On the left side, we have A number of potassium atoms. On the right, we have D. So for it to balance, A has to equal D. Easy. How about oxygen, O? On the left, we've got 4 of them in that first compound, so that's 4A. On the right, it's only in water, so that's F. So our rule is 4A equals F. You just do this for every single element.
Now comes the puzzle part. Now, the full substitution can be a little long to show here, but the basic idea is you plug one equation into another to get rid of variables. You keep going until you've boiled it all down to a simple relationship between just 2 letters. In this case, it all simplifies down to this. 5 times A must equal 2 times E. From here, we can just pick the simplest whole numbers that work. So let's say A is 2 and E is 5. That's our anchor. Once you have those first 2 values, you can plug them back into all your other little rules and solve for all the other letters, one by one. And there it is, a perfectly balanced, incredibly complex equation, solved with absolute certainty. No guesswork needed.
Okay, so we spent all this time finding these numbers, right? But what do they actually mean? This, right here, is the real aha moment, where this whole thing goes from being just an exercise on paper to something real and incredibly useful.
So let's take this number 2, for example. What is it really telling us? It's not just a random number to make the math work out. It means something very specific.
It's a recipe, a chemical recipe. Those numbers, those coefficients we worked so hard to find, they represent a ratio, specifically a mole ratio. Now, a mole is just a chemist's way of counting huge numbers of atoms, kind of like saying a dozen when you mean 12. So this recipe is telling a chemist, hey, for every 2 moles of magnesium you use, you're going to need exactly 1 mole of oxygen, and you will produce exactly 2 moles of magnesium oxide. This is how we predict and control what happens in the lab. So you see, balancing an equation isn't just about math. It's about proving that fundamental law. Nothing is lost, it just gets rearranged into something new, which kind of leads to a pretty cool final thought, right? The very atoms that make you up might have once been inside a star or a dinosaur. They're just cosmic recyclables on this endless journey. The universe, in a way, is the ultimate balanced equation. Thanks for watching.